Okay, let's get started. Just a couple of short housekeeping notes, and then we'll spend most of the time today talking about lecture. Let's talk about the assignments at for a moment, and let's also talk about. I'll just choose assignment 6 here as an example. I apologize for a little detail that I overlooked in Reddit, which is on my Reddit feed. For all of the URLs in the actual instructions, there's a little tag next to them so I can open or close that tag right in line. And I thought that was default in Reddit, and a student pointed out to me that it is not. So I apologize if you spent hours on end flipping back and forth between different tabs in the instructions and so on. So I did a little bit of homework, and I realized that this is coming from the Reddit Enhancement Suite. So if you don't have RES, download and get that going. It's a plugin for your browser, and then hopefully it will help you with the assignments. It'll speed things up so that you can sort of open things in line and not have to be switching between tabs and windows and so on. So I realize that might have been a little frustrating. My apologies on that. Okay, another issue that was brought to my attention is deep copy. So if you'll recall, you've got I think all of you now have a population of individuals. Oh wait, the undergrads, you're still on the hill climber, right? Not the parallel hill climber yet. So you have one individual, you deep copy that individual and then mutate the child, right? So we're using the deep copy library, which is supposed to recursively go down through a class instance and copy all of the variables and all of the class instances if there are any inside that class instance. As the name implies, it's supposed to do a deep copy. There seems to be a little bit of confusion that when it does do a deep copy, does it actually copy the references or the values themselves? So, for example, if we have a parent here, and this parent, remember, has a fitness and a genome, which is a vector or matrix of all of the synaptic weights. When you deep copy the parent and create a new child, the question is it actually creating a new instance of fitness and genome, or is it copying just a reference in which these still point backwards to the originals? At least in my version of Python and my version of deep copy, I'm copying the values and not the references. Why does this matter? Why do we care whether it's copying values or references?
You can change the reference value.
Right, so if we mutate a synaptic weight, so now we have G prime, we have a difference in here, we want to make sure that we're just modifying the genome associated with the child, and not, if this were pointing back to here, that this would also be modified. We want to make sure that the parent and child have separate genomes. On my platform, that is definitely the case. I would suggest that all of you check this and make sure. So make a copy of parent, make a mutation to the genome, and then print the genome in the child and print the genome in the parent, and they should be different. If they're not, then somehow there's something going on with your version of deep copy and so on. So if you see that the genomes are the same after you've mutated just the child, go back and check your version of deep copy and make sure it's actually copying the values and not the references to these variables. Make sense? Okay, one student seemed to have this issue, which suggests there might be others. I'm not sure why the difference, but just check this. Okay, any other questions about the assignments? Final project. Graduate students, you're thinking about what you want to do for your final project. As I mentioned last time, it's okay if you propose something that's somewhat ambitious as long as you're able to break this down into weekly deliverables. That's really the challenge at the beginning of the final project, is to think carefully about, if you want to try and get to this final goal, how do we break this down into a simple deliverables as possible. Yes?
I was thinking that if I cannot make it like after 2 weeks, then am I able to change my goal?
Okay, that is a good question. So what happens if partway through your deliverables you want to change your goal or change some of the deliverables? That's perfectly fine with us. So you're not being assessed on your ability to maintain all of the 9 or the 4 deliverables that you posed up front. What we're looking for is that you're thinking reasonably about your project and you're making reasonable progress towards your goal. If in the process of doing your deliverables you change your goal as well, that's perfectly fine. Just make sure that it's actually in the deliverable. So when you submit the deliverable, you say, I know in deliverable 3 I promised X, but I'm now delivering Y because I'm now trying to get my robot to do this. I've changed my goal. Just make sure that you let us know from week to week where you're going, right? You can modify your deliverables as you go. That's perfectly fine. Any other questions about assignments or final project? No? Okay, so back to lecture. We're working our way through this series on minimal cognition here. If you remember all the way back to the beginning of the course, we were struggling with this issue of how to actually define intelligence. Those of us that are operationalists believe in the Turing test. So there is no real good definition of intelligence. We know that we will have created an intelligent machine when, in the case of the Turing test, it might be able to hold a reasoned conversation with us. What we're looking at in the minimal cognition experiments is what's sometimes now called the physical Turing test. So imagine you have an animal, or in our case a robot, that may not actually be able to speak, may not be able to hold a conversation with you, but the way that animal or that robot is behaving suggests that it's intelligent, right? So from the Turing point of view, we're always focusing on behavior. Behavior might be holding a conversation, or in our case, it might be a physical behavior of doing something in the physical world, right? Okay, so if we're trying to create robots that exhibit intelligent behavior, we're still back to this question of what exactly do we mean by intelligent behavior? Well, there are certain aspects of intelligent behavior, certain building blocks that we would expect to see in any human or animal or robot that claims to be intelligent. In lecture 9, we're going to look at 4 of these. We looked at the first of the 4 last time. What was that intelligent behavior? If you want to be able to get around intelligently in the real world, you're going to have to be able to...
Well, we looked at a robot that could determine whether or not it could fit between 2 blocks.
We were looking at this robot to determine whether it could fit between 2 blocks. That task is a specific example of a cognitive building block. Affordances, being able to perceive affordances, right? As I look around my environment right now, I see lots of complex objects in my environment, but as I look at them and consider them and try and figure out what they are, I'm thinking about my possible interactions with them. There's an object here that might be able to support my weight. I might be able to sit at it. There's another object here that I might be able to rest something on and write something on. There are other objects out here that I might be able to have a conversation with. There's another object out there which is advertising the affordance of leaving the room, and so on, right? So in order to get around in the world, you have to think about what opportunities or risks or roadblocks are being thrown up by the objects in your environment. What functions do they afford you, right? It's all about you when we're talking about intelligence. Okay, so that's the first one. So in lecture 9 and lecture 10 today, we're kind of in the boiler room of robotics now, right? We're really trying to create robots that exhibit these building blocks. And later in the course, we're going to talk about how a robot might start to put these together and use them in different ways. Okay, we may or may not finish lecture 9 today. We're a little bit behind. That's fine. Hopefully we'll move on to lecture 10 today when we're going to look at a 5th building block of intelligence called active categorical perception, or ACP. We'll see ACP pop up again several times in the remainder of the course. Okay, so back to lecture 9. We were looking at this robot that was evolved to perceive affordances. And as was just pointed out, We tried to create a minimal environment in which to evolve a robot capable of perceiving affordances. We have these pairs of blocks that are falling, and we've formulated a fitness function on the right that selects for robots that will perceive the affordances in the way that it will consider the width of the gap between the pair of objects relative to its own body. Okay, and we saw that we were able to evolve a robot that does so, but we saw last time that sometimes it makes mistakes, right? And in retrospect, that's not so surprising. It tends to make mistakes when this evolved robot is exposed to environments that it never saw during the evolutionary process, right? This is the $10 billion question in AI. How well is an AI or a robot going to do in the real world when for sure it's going to experience situations it never saw during training or during evolution? Okay. All right. Let's move on to the second of our 4 cognitive building blocks. This is self, non-self discrimination. I know that this thing out here in my visual field is me, and all this other stuff is not, right? Seems like kind of a trivial thing to do, but we all had to go through this process when we were very young, right? At some point, our body ends and the world begins. Where is that point? We've actually already seen a robot that learned to distinguish between self and non-self. What was that robot?
I forget his name, but he would move his hand when he touched anything that was moving. He would know. He could see.
That's right. So it was BabyBot, right? So BabyBot would move its hand into its visual field. It could detect motion and stationarity. That's it, right? And so it would see that whenever it sent commands to the motors, there was this shaped blob, right? That shaped blob was it, because whenever it moved, whenever it sent commands, it would see that moving, and when it didn't send commands, it wouldn't see that moving. A good strategy for discriminating between self and non-self. But they made things easy on BabyBot, which is that there was nothing else moving in its environment, right? Unfortunately, as we're learning, we don't always have that luxury. If we're in the real world, there is usually stuff that is in motion, right? Even though most of you are sitting quietly, there is still motion in my visual field. How can I distinguish between this motion and the motion that I see out there? Okay, so let's again try and create a minimal environment to see whether we can evolve a robot that can distinguish between self and non-self. We now have a stationary robot, and it has one motor neuron, and that one motor neuron is going to rotate its arm relative to its body. So it's got this little stick arm and this little ball hand, and as you can see in this figure here, the hand will block the robot's view, right? The hand can actually block some of these ray sensors emanating from the robot. They also drop a single object now from the top of the screen, and this object may fall straight down, or it may fall at a diagonal, it may fall at different rates, and the robot needs to be able to see this object, and it needs to be able to move its hand so that when the object collides with the robot, and all the dropped objects are always angled so that they'll hit the robot when they land, the hand has to collide with the object. So in essence, they're going to evolve a robot that can catch, quote unquote, this falling object, right? From our point of view, this looks like a trivial thing to do, but remember, thinking about thinking is misleading. We need to put ourselves in the shoes of this robot. This robot gets back at every time step 1, 2, 3, 4, 5, 6 numbers. So we've got 6 ray sensors, 1 motor, remember? And the length of these rays change over time. How is it going to know where the object is, where self is, where the hand is, and make sure that it gets the hand to the right place at the right time? Okay, tell me about the fitness function at the top right there. So theta sub I here is the angular error between the object and the robot. So when the object actually hits the robot, it hits the robot at a certain angle, and the arm has to be at the same angle, right? That's catching the object. There's actually a typo in the paper itself. It had max in there. I contacted the author. It should actually be min. Tell me about this fitness function. How does it select for this desired behavior? So the first part looks pretty familiar, right? We're going to evaluate each controller several times. We're going to evaluate it num trials times. We're going to take the average ability of the robot in each of those environments. What about the individual performance criteria, P sub I here? Why 1 minus?
Because when theta is higher, P sub I would be lower.
Exactly, right? So when theta sub I is higher, P sub I should be lower, right? The 1 minus is a clue to you that this term over here is a penalty term, right? The more of this, the worse the fitness is going to be. Okay, so why min theta over 4, pi over 4 theta sub I?
So it's just if the angle is less than 45 degrees, then I want to take the minimum difference of that, I guess.
That's right. So if the angle theta sub I is greater than pi over 4, just don't worry about it. Pi over 4 is the worst you can possibly do, and by doing that, we can then divide by pi over 4 and make sure that the right-hand term there is always going to range between 0 and 1, which is good because we're going to subtract it from 1, right? So we now are sure that P sub I is always going to range between 0 and 1, where 0 is the worst possible thing the robot can do, and 1 is it captured the object. Why absolute theta sub I?
Because it starts in the middle.
Not because it starts in the middle. Theta sub I is the angular error. It's the angle between where the object hit the robot and where the arm actually was.
Because the negative angle would give you a positive, like a over 1 value over 1.
Yes, that's right. That's part of it. Yeah, that's right. So they still want to keep it normalized between 0 and 1. And also, it doesn't matter whether the robot missed the object to the left or missed the object to the right. Right? Both of those are bad things. So it doesn't matter, right? So we're just trying to minimize theta I. We want the robot to achieve a theta sub I of 0 in all conditions. Grab the object, grab the object, grab the object. Make sense? Okay, so again, we're not seeing the actual evolution. They ran evolution and they evolved a robot that could successfully catch the object. And by doing so, it had to also solve the non-self discrimination task. Its hand is moving across its field of view, breaking the beams. While that's happening, the object is also falling and breaking the beams. And the robot has to be able to somehow distinguish between those two things and get the arm to the right place. This figure down here is again showing us the performance of the single best evolved CTRNN out of all of the CTRNNs they evolved. How do we read this? Well, on the horizontal axis here, we have the final object angle. So minus pi over 8 means the object hit on the left side of the robot, plus pi over 8 means the object hit on the right side of the robot. And where was the robot's arm in those conditions? When the object hit to the left, where was the hand for this robot? It was to the left, right? So the vertical axis is showing the angle of the arm. So when the object hit to the left, the arm was to the left. And when the object hit the robot's right side, its arm was over there on the right to catch the object at exactly that moment. How well did this robot do? Pretty good, right? As you would expect, all of the points here are falling along the diagonal. Again, these bars here represent error bars. So for example, let's look at the cases where the object hit the center of the robot. They dropped it from different horizontal positions at the top of the screen. So the object was coming in at different angles, and they all hit at the same point. So we have multiple environments. How did the robot do in those situations? What is the error bar telling us? What is the fact that there is an error bar at all? Why isn't the error bar like this?
It seems to be within plus or minus pi over 32 degrees of the ball hitting.
That's right. So the object hit the robot front, and the arm was always between plus or minus maybe pi over 32, right? It wasn't perfect, but it did pretty well, right? If the robot had been perfect and got its arm exactly vertical when the object hit exactly vertical, these error bars would have been squashed, right? Tell me about the error bars across this figure.
Is the falling object infinitesimal in size?
It is not clear from this, and I've read this paper many times. It's also not clear. I'm going to trust the picture here that the object actually had a radius, and it was probably the same as the robot itself. Right? If it was infinitesimal, it would be hard to break the beam. I mean, it might break the beam for just one time step before moving on, but I think the object actually does have an appreciable size.
So would like hitting the object on the side after it passes through the bubble?
That probably, it depends on when they actually took this measurement, right? I think it's probably when the object hit where the hand actually is,
Okay.
I think. But again, it's not too clear from the paper. Yep.
So it looks like the error bars fluctuate at the extremes in the center, but in between they're minimized.
That's it, right? So you can see the error bars are a little bit shorter in these regions here, meaning the robot's much more consistent in these conditions. It's a little bit more error prone when the object hits exactly center and also when it's at the extremes. Not exactly clear why that's the case, but again, we can see a robot that's doing really well, but not perfectly. Okay. This is probably the most non-intuitive figure you're going to see in this entire class, so we'll take our time with this one. It always takes me a while to explain it because I get a little bit confused, so we'll go slowly here. Again, this is the figure from just one evolved C-N. It's this one. And this figure actually shows you how the robot moved its arm in multiple environments. Okay, here we go. Let's start at the bottom here. We're going to reference this angular position up here. You'll notice that all of the lines, the trajectories are coming down and converging at the center point, which is an angular position of 0. So each one of these trajectories corresponds to one drop of the object. And in all of those drops, the object fell and hit the robot on its nose, right in the center, right? Like the picture we just saw. Okay. Why do some of the trajectories start on the left here and the other half start on the right over here?
Is that where they initially start, the drop initially started?
That's it. So in half of the environments, they're going to drop the object minus pi over 8 radians to the left of the robot. And in the other half of the cases, they're going to drop the object plus pi over 8 radians above the robot. That's what the initial position, the initial starting points of the trajectories represent. The shading, the grayscale of each trajectory, shows the initial angle of the arm. So before they placed the object and before they dropped the object, they took the robot's arm and they rotated it to a certain angle. Right? So let's have a look for a moment at this light-colored trajectory, the lightest colored trajectory that comes down through here. We know that the object was placed at minus pi over 8, so to the left of the robot. The light shading corresponds to the light shading up here. That means they then took the robot's arm and dragged it to plus pi over 8. So the object is up to the left, and the arm has been dragged to the right. They drop the object and turn on the robot's CTRNN, and the arm starts moving. Tell me about this light-colored trajectory over here. Which situation does that correspond to?
The initial thing falling from pi over 8 and the arm staying at pi or starting at pi over 8?
That's right. So the trajectory starts over here, which means the object is to the robot's right, and the light shading of the trajectory means they also drag the robot's arm to the right, and then started the simulation. Tell me about what does it mean that all of the trajectories converge down to around the center point here? What does that tell you?
They're making it possible for the robot to catch, or it's like a stationary robot too.
The robot is stationary, right? Only its arm rotates. So what do we know about the robot in these conditions?
In the center.
It's the arm is eventually at the end is at the center, and I just told you that in all these drops, the object is always falling diagonal and hits the robot on the nose in the center. So the robot is successfully catching the objects in all of these conditions. How did the robot catch these various objects? Tell me about its strategy.
Something I just noticed from the graph, which might be related, is when the initial position of the arm is the same as the initial fall, the squiggles,
Yep.
the scientific term squiggles, stay at that side. So like the far left has really dark squiggles and the far right has really light squiggles.
Yep.
So
But what does that mean?
it seems that
What's going on? Let's just focus on the dark trajectories over here on the left. What does that mean? What's happening?
when the ball's falling from the left, the arm, I don't know if it notices it, but it stays over there and kind of moves back and forth trying to detect it.
Exactly. So the object, we know the object has been dropped from the left, and the trajectories over here are all dark. So the dark trajectory means the arm is over to the left. What is the fact that the trajectory is oscillating tell us?
It's balancing, maybe?
What's that?
It's balancing out while it's catching it?
It's doing something. Remember, the object is falling, so it hasn't actually touched the object. It's not balancing the object. And I guess I didn't actually explicitly say this, but the objects fall in a straight line. So it's not the object that's oscillating, it's the arm itself, right? So the robot has actually sort of moved its arm to where the object is and then is sweeping its arm back and forth like this. Why might it be doing that?
Trying to detect which one is the object and which one is its arm.
Okay, so it's trying to detect, I'm going to put scare quotes around all of the nouns in that sentence, right? Where it's hard to say exactly when and how and so on, but something like that, right? Remember that BabyBot was able to distinguish self from non-self through motion. When I send a command, there's a change in my sensory stimulation, right? So there's something that's going on. It's more complicated here because as our minimal agent here is waving its arm back and forth, it's breaking the ray sensor beams. But the object is also falling, which the robot can see, and it is also breaking the beams at the same time, right? So it's not as simple as I'm gonna send a motor command and I can see this thing moving like crazy, and everything else is more or less stationary. So the stationary stuff is non-self, and the moving stuff is self, right? It's more complicated here. But there's something like that going on, right? The agent says, when I move my arm like this, the beams tend to break in this way, and I subtract that from the other ways in which the beams are breaking, and that difference, that's probably the ball, and the ball is falling at this angle, so I'd better get my arm to this angle, right? Did you have a question?
I was going to just mention how it's probably trying to detect the ray since the arm's in the way.
Exactly. So you can see that in all of the trajectories here, there's quite a bit of waving back and forth, right? Which again makes sense. So in developmental psychology, with the study of human children, they talk a lot about motor babbling. So if you've ever watched a young child, they move around like crazy, right? And part of that motion generates useful information, like, for example, distinguishing between self and non-self. You'll notice some other interesting patterns going on here. So for example, let's take the dark trajectories again, which correspond to the arm off to the left, and trace them back to the beginning here. So the arm is to the left, the object is to the left, and the robot actually moves its arm to the left. It's almost out of the way and then back again. It does exactly the same thing in the light trajectories. So in the light trajectories, the object is still up and to the left, and the arm is off to the right, and the robot makes exactly the same movement. So it starts in both cases by sort of doing the same thing, and then there is some sudden point at which the lines start to diverge. What do you think is going on at these points in time where the trajectories diverge, not converge? What's happening there?
The object just entered the robot's field of view.
It's possible, right? So again, it's not clear from this explanation, right? Maybe it just couldn't see the object up until a certain point. I think in this case, it actually could see the object in all the cases, right? So it is the only thing that's happening in this robot's environment, aside from its own hand, is the object, right? So the object is causing this divergence in trajectory of the arm. So the robot is now starting to change what it does in response to what it sees. Now, whether it's made a decision about where the object is going to hit, it's hard to say, right? You'll notice that actually up until just a few moments before the object reaches the robot, the arm is far from, in many cases, the arm is far from zero. So it's sort of waving its arm out here. The object is coming down, and just at the last moment, it moves its hand to the right place. So presumably, the robot has already made the decision of where the object is going to hit, and it's maybe just biding its time until it gets there, and then off it goes.
It seems like in the beginning, I'm probably halfway, it's trying to find the distinction between the arm and the ball, and then eventually it realizes having its arm in the way is too much noise, so it moves it out of the way.
Possibly.
And just watches the ball.
Again, possibly, right? So at least by this point, in most of the cases here, the arm is out of the way, right? It's maybe trying to get a clearer view of the object and then bring the arm back just in time. But that's not true of all the trajectories. Some of them it is waving its hand in front of the object just before the object hits, right? It's complicated. And again, this is a minimally complex robot, right? Already, we get some relatively interesting and rich behavior out of this robot. You could imagine creating a dozen more plots just from this one robot to try and disambiguate between these various hypotheses we've been formulating. Okay, but at least we do know we have a robot that can distinguish between self and non-self. Let's move on to a third building block. This one, for sure, we know that any intelligent agent is going to need, which is memory, right? Remember something even if you can't see it or it hasn't arrived yet in time. It's a future event. Okay, how do we select for a robot that's able to remember things? Well, that's easy enough. Take things away during behavior, right? So we're back to our little Space Invader robot here. 2 motors that control 2 rockets horizontally, so this robot can shuttle left and right along the bottom of the screen. Again, we have a single object that can fall at different angles and different velocities. We've got our ray sensors again, but you'll notice now that the ray sensors are dotted rather than solid lines. That is a visualization that indicates that the moment that the robot starts moving, the sensors shut off. So the moment the robot starts moving, we put a blindfold around the robot and it can no longer see anything. All of the sensor neurons are capped at 0. So what does the robot have to do? It has to remember not only where the object is, but have a prediction about where the object will be. Why does it need to have a prediction for where the object will be? The fitness function on the right should give you a hint about what this robot is supposed to be doing.
Because it needs to land where the object is going to land, not where it was when it last saw it.
Absolutely, right? So the fitness function in this case, again, we're going to take an average over a number of trials, and we're going to take the average d sub I, the horizontal distance between the robot and the object when the object hit the ground. And I don't know why it's 200. This must be some sort of normalization thing. But it's 200 minus, which tells us that we're trying to minimize theta sub I, right? So the best thing this robot can possibly do is get all of its d sub i's equal to 0, right? Be where the object is when it hits the ground. Okay, make sense? All right, so again, here's a figure of the best evolved robot using this environment and this fitness function. Tell me about this evolved robot. How well did it do? Was it perfect? Did it get a D sub I in every case? Definitely not. Where did it have a hard time?
Negative 40 and 0.
So again, we see at the extremes, it had a hard time, which, as we'll see in a moment, kind of makes sense. But it also seemed to have a hard time when the object actually landed in the center of the screen, center bottom of the screen. Again, not immediately clear why, but probably they didn't include some cases here, so the robot wasn't able to generalize very well under those conditions. Okay, thankfully this one's a little bit easier to read than the last one. Same thing though, right? We're looking at one evolved robot. So we have the horizontal position here of the robot for vertically falling objects. This is actually, horizontal position is, they didn't label this very well, it's horizontal distance. So a horizontal position of 0 is the robot ended up where the object hit the ground. Vertical axis is vertical position, so you can see they dropped the object from the top of the screen at these different horizontal positions. What can you tell me about what the robot did in these conditions? What is the fact that between 175 and 170, all of the lines are perfectly vertical? What does that tell you about the robot and the object?
Haven't interacted with it.
They haven't interacted yet, but we can know something even more specific than that.
The robot isn't moving yet.
The robot isn't moving yet. How is the object moving?
Down.
Straight down, right? So the object, all of these object drops, the object was falling straight down, right? And the fact that it's vertical means the robot isn't moving yet, right? It's watching, but it's choosing not to move because it knows the moment it moves, it's going to go blind, right? So this controller, this CTRNet, has evolved to suppress signals to the motor neurons. The motor neurons, or the rockets, are receiving values of 0, right? Hold steady. And then at some point, something happens that the motors start receiving non-zero values and the robot starts moving. This robot actually hit on a pretty simple idea. This is one of the few exceptions where you can actually figure out from the behavior what the controller is probably doing. Let's start with behavior. Clearly this robot does capture the object. It gets there. How and when does it get there? Does the robot get to the object? Does the robot get under the object before the object hits? If the ray sensors are broken, move towards them, right? That's it. That's the heuristic. So let's have a look at one of these conditions. Let's take the leftmost black line here. So this means that the object is top left. Remember that there's this fan of ray sensors. The object is falling. It is inside this fan of ray sensors. So the left ray sensors are broken by the object. They're broken, broken, broken. The object keeps falling. And it falls below, we're doing the one on the left, it falls below this fan. So suddenly the left ray sensors extend to their full length again. The moment that happens, move at a constant velocity to the left, right? you'll notice that these diagonal lines aren't oscillating like the previous robot, right? The robot is moving at a constant rate to the left, right? Same thing on the right. When the object falls vertically from the right, the ray sensors, the right-hand ray sensors are broken, broken, broken. Suddenly they extend to their full length again, move to the right. A beautiful, elegant solution, right? If you were to write this in code, it would be like three lines of code, 4 lines of code. And it's a general solution, right? If the object is closer to your midline, then the object is going to stay inside of your cone of perception for a longer period of time. And then towards the end, just before it reaches the ground, just at that point does it fall outside of your cone, and you only need to move a small distance to the left and catch the object, right?
So does the agent move horizontally at the same rate the object is falling?
That's a good question. It's hard to see from the axes here, right? So the lines would have to have a slope of 1 or -1
Yeah,
to see that.
They're fanning out at 45 degrees, but I couldn't really tell from the image.
You can see at least that all the diagonal lines here have the same slope. So it was always moving at the same velocity relative to the object. I'm imagining that they probably dropped the object at the same vertical velocity in all of these cases, which means the robot is always moving at the same horizontal velocity. But I can't tell from this picture if it's a slope of 1, maybe. Right. Pretty straightforward. Okay, so the black lines here are supposed to show you the cases where the robot actually caught the object, and the gray ones indicate it got close but didn't quite catch the object. Why not? What's happening here? You can see now that these gray lines, if you follow them up towards the top of the screen, they're either at the center or the left and right edge. Let's talk about the left or right edge. Why does the robot have a hard time in those cases?
Did it never enter the cone?
It had to enter the cone, right? Because it's definitely moving. Something is triggering the movement.
You can see, I remember it was like over below 40 or -40, so you can see that there's no trials that are above or below them.
There's no. So these actually are trials here, right? So it didn't do very well at them.
Was it not nearly enough time to remember exactly where it was?
It wasn't enough time to remember, right? So whatever it was, the object was only in the robot's cone of perception, right up in the top corner for a very short period of time. And maybe it wasn't enough for the CTRNN to do whatever the CTRNN does to say, okay, the rays are broken, now they're unbroken, start moving, right? Makes sense, right? We sort of flashed the object for a very brief period of time, and it had to make its best guess about what to do under those conditions, and did pretty well.
It also looks like it couldn't go fast enough for the farthest edge ones. If it moved at a constant rate, because the line never reached where the black line was. If you look like to the far right one, the farthest right one.
The farthest right one,
It's
this
like
gray one?
Yeah, it's parallel to the black line.
Yep.
Which just looks like it couldn't get there fast enough.
That's a good question. This robot could move much faster than it actually is moving, right? This is an evolved response. It's just that for the simple heuristic, it's chosen to always move at the same rate. Okay. So this is for the evolved robot in conditions where objects are falling vertically. What happens when they fall diagonally? So now we're going to have objects that are falling diagonal, and again, they're hitting the ground at different horizontal positions, and we want to see where the robot was. How did the robot do in these diagonally falling conditions? Diagonally falling object conditions.
Not awful. Not great, but not awful.
Not great, but not awful. It's having a harder time, right? And again, this is a pretty challenging task, right? You can only see something for a short period of time. You got to decide where it is, how fast it's falling, what's its angle, and get there when it gets there. Okay. Here's again a picture to show you what this looks like. So let's take that evolved controller, drop the object from a whole bunch of horizontal positions at the top of the screen, and they're all going to fall to the right. What did the robot do in this case? Same robot.
Waited for it to leave the beam and then started moving.
Well, again, see, it's got the same heuristic, right? The object leaves from the right-hand edge, leaves the robot's cone of perception, and it starts moving. But now, how does it move? It's not moving at a constant rate, right? It's kind of jigging to the right. And it does okay, but the spread is pretty wide here, right? Not doing great. All right, let's drop a whole bunch of objects from the center line, but let's drop them with different diagonal trajectories, and we see the same sort of thing, right? The robot holds still until the object leaves the cone of perception, and then it starts either jigging to the left or jigging to the right, and more or less catches it. Right? Okay, so just some visualizations of how the robot solves this task, which is a good one, right? You don't want to remember, the robots and evolution is kind of lazy, right? Comes up with a good sort of first order approximation, which is watch, 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 and the moment you can't see something anymore, why stay stationary? There's nothing more to see, get moving. Any questions about that? Okay, let's move on to the fourth and final one. This is my favorite one, selective attention. And I actually had a student who worked on this last year. If I can find it here for you. Cart. All right. So I had a student who actually did implement this last year in a physics engine. This is selective attention. This is sort of interesting in that it kind of, it's more challenging than the first three. There's a lot of things going on in selective attention. You've got two objects you need to deal with, so difficult like the affordance case. But these objects are independent of one another, tricky. Some of them are falling faster than others, and they're hitting the ground at different positions. So what does the robot need to do to succeed at this selective attention task?
Calculate velocity and trajectory.
Possibly, right? So again, we don't know whether it actually needs to know the velocity and trajectory. It needs to infer it somehow.
Needs to catch both objects.
Needs to catch both objects, but in order to catch both objects, again, it has to sort of mentally juggle a lot of things here. We've already talked now quite a bit about the various building blocks of cognition. What are the building blocks of cognition that it needs here to solve this task?
Memory.
Memory for sure, right? So look at this frame here, right? This robot in a moment is going to catch this object. It can't see it. So it has to remember somehow where it is, how fast it's falling, and what direction, and get there. So memory is important. What else? If you remember back to the beginning of the course, right, we were brainstorming about all these different building blocks of cognition. Some of those building blocks are not just the three that we just talked about. Memory is important. What else?
It needs to be able to choose which puck is priority.
There it is, right? It needs to choose which puck, right? So at the beginning, when both of them are dropped, let's see. When both of them are dropped, actually, this is a good case, right? One of them is actually closer to the robot. In this case, it actually only sees that one puck. Now it sees both. What's going to happen?
How do we see both? It looks like it's just a wide puck.
It's hard to see, but there are two beams that are hitting this puck, and a third beam is hitting the back puck.
It has to be able to calculate the distance from the puck.
Sorry?
It has to be able to calculate the distance from the puck. The beam does.
All it has is the lengths of these beams. That's it. Okay. What does it have to do at this point? It has to choose, right? What's happened in this case? This is a particularly challenging situation. Why?
The
The right puck is going faster, right? So it has to actually catch the right-hand puck and then go get the left-hand puck. But an instant earlier, the left puck was closer to it, right? So it can't rely on some simple heuristic like go after the closest puck, right? If you've ever heard about the marshmallow test, right? They do this with children all the time. They put one marshmallow in front of the child. They say you can eat the marshmallow now or you can wait. And if you wait, we'll give you 2 marshmallows, right? So it's hard to get through this life if you always go after the one marshmallow that's in front of you, right? From time to time, if you're paying attention, you realize that there's some other event that is more distant from you in space and time. But that distant event is perhaps more important than the immediate object, right? So it's tricky for humans, tricky for robots, right? Okay, that's the selective attention task. So I love this one because, again, it's very minimal, simple environment, simple fitness function. But in order to solve this one, the robot is going to have to assimilate a lot of these building blocks of cognition. So the overall building block we're talking about here is selective attention, right? The robot, it has to switch, again, with air quotes around all of these, has to switch its attention sometimes from one object to another, right? You need to do this all the time in your daily life, right? You can't just attend to whatever is immediately in front of you. You have to intelligently decide when to pay attention to my voice and when to pay attention to the fire alarm that supersedes whatever we're talking about at the moment here in the class. Okay, so you sort of all already seen how this works. Again, we've got our rocket robot down here at the bottom of the screen. These 2 objects are falling from different initial conditions, and they're falling at different velocities. We're going to sum up, we're going to take the mean of its behavior or its performance in each of the ith environments. We've got 200 minus. So we know that the robot is being, the controllers are being selected to try and minimize P sub I. P sub I is the sum of these 2 components. What are these 2 components?
I have a quick question about
Sure.
the equation.
Yep.
So how can the user decide that it is should use 200 at the front to maximize the fitness value?
How does the robot maximize the fit?
How can the author decide that in order to calculate the fitness, he should use 200 instead of like 300?
Oh, you're right. So why 200? It probably has to do with the distance here. So probably the worst thing you can do is have an object hit here and be here as the robot for the first object. Second object hits here and you're over here, right? That's the worst possible thing you could do. That'll give you a very large D1 and a very large D2, and those 2 things together probably sum to 200 in the units of distance in this world. That would be my guess.
So do you want to detour the distance from each individual?
The distance from the first object and the second object. So the fact that it's 200 rather than 300 or 100 doesn't matter for our purposes, but it's probably to normalize this, this fitness function somehow. Right? So it's always positive.
So like the x-axis is probably like 100.
Something like, yeah, that would make sense, right? Yeah, exactly. Horizontal axis is 100, so the worst thing you can do is be 100 units away from each of the 2 objects when it hits the ground. Okay, so D1 and D2, horizontal distance between the object I, sorry, that should be object I's final position and the agent's final position at what time step? When do we calculate D1 and D2? Remember, we've got these 2 independently falling objects.
When they pass where the robot is?
Exactly, right? So at the moment that object 1 hits the ground, calculate D1, how far was the robot from object 1. And then when object 2 hits the ground, calculate how far the robot was from object 2 at that point in time. And those points in time are going to be different in different environments, right? So what's the best thing the robot can do in terms of the fitness function here? Catch both, which would give you D values of what? 0, right? Exactly. Be where the objects are when they hit in both cases. Both of your D's are 0, P sub I is 0, best thing you can do, so you're subtracting nothing from 200, right? Best thing you can do. Okay, so again, we can now start to break down this problem from a behavioral point of view. So there are really two sorts of problems that this robot can face. The first is the passing objects problem, which we just saw in the video, right? The object which is initially further away, the 2 marshmallows, right, ends up being the one to hit first. You should actually, if you're attending to or paying attention to the closer object, at some point it's going to have to switch its attention to the faster moving object and go grab it, right? So it's going to have to selectively change its attention. And then there's the object permanence problem, right? This is where the memory part comes in. As you're chasing one object, by doing so, the other object may pass outside of your cone of perception, right? This robot isn't omniscient. It can't see its entire environment all the time, right? And this is challenging for us as well, right? You get a notification on your desktop that there's an email, you go and check it, you forget what you were doing a moment ago, right? Distraction. How do you remember and go back to what you were doing before when it's no longer visible because you've selectively chosen to attend to some other situation? Okay. All right. This figure also takes a little while to work its way through. What you're looking at here in these 5 figures is, again, a single evolved robot dealing with 5 different environments. Each figure corresponds to different environments, and we have not PO and not OP, or not PO and OP. So we're going to try and create environments which create or remove either of these 2 problems. So the first of these 5 environments is pretty simple, in which the robot actually never experiences the passing objects problem or the permanence problem. Then we'll get to these 2 cases down here where the robot is going to have to deal with both problems at the same time. Okay, let's start with trying to figure out these figures. What do the straight black lines mean in all 5 figures?
Because the horizontal position of the object catching.
It's the position of the puck. Yeah. Right. So the straight line, that's showing you how the puck is falling. So in this case, object 1 is falling like this, and in this case, object 2 is falling like this. You'll notice that object 1's line ends higher than object 2's line. What does that tell you?
Caught first.
It may or may not have been caught. In this case, it was caught.
Object 1 was moving faster.
Not necessarily.
Object 1 was placed closer.
Also not necessary.
Touch the ground.
Touch the ground first, right? So the fact that the line ends higher, the vertical axis here is time, right? So as the objects are falling, all we know is that object 1, which for our purposes will be the lighter shaded region, hit first, and then sometime later, object 2 hit the ground. We don't necessarily know from this which one was placed higher originally or which was falling faster. That's actually not shown in this figure. What is the third black line, the squiggle, show you or represent?
The agent's position.
The agent's position, right? So that's the movement of the object of the movement. Why these trapezoids? What is the shaded region is a trapezoid. Why is it a trapezoid? What is the shaded region telling us? We know one is associated with object 1 and the other one is associated with object 2, but what is that shaded region?
Relative field of view.
Field of view of
Content being caught.
of the robot, right? Why is it tapering as the object falls?
Because that's how trapezoids work.
What's that? Because that's how it is a trapezoid. But what is that telling you about the robot's perception and its behavior? Why is it narrowing?
The ray sensor freaking shorter as the object's getting closer.
The ray sensors are getting shorter, but that's actually not what's being represented here by the narrowing of the shaded region. You gotta think carefully about this one.
Where the object can actually see where the agent can actually see the object gets narrower.
Bingo, right? Where the agent can see the object, right? So as long as the agent is anywhere in this horizontal position, at this point in time, it can see the object, right? At this point in time, the agent has a wider range where it can move and still see the object. Why is that the case? Why does its field of view narrow as the object gets closer to the ground?
Just because of how the angles.
Because how the ray sensors are arranged, the geometry of the ray sensors, right? So obviously if the object is up here, it's got a broader view, but as the object is closer, it's got to move so those ray sensors hit the object, right? There's a much narrower window through which it can see things. So this robot doesn't go blind, but it does get harder to see the object, or there's a narrower range of motion, narrower range of positions that will allow the robot to actually see the object. What does it mean when the squiggly line is inside one of these regions or outside one of these regions?
It's visible.
It's visible or not visible, right? Okay, so that's enough for environment one. What does the robot do in this environment? This is like color commentary for sports, right? Talk me through what the robot did in this environment.
For the object that took less time to reach position 0, I'm just going to call it the ground position 0.
That's fine.
For the object that took less time to reach position 0, it squiggled back and forth until converging with it.
Yep.
And then moved over and squiggled to the left of object 2 until eventually just squiggling around it a bit.
Followed it and then caught it, right? So here's the moment when the robot caught the lighter object. Let's talk about the lighter and the darker objects, make things simpler, right? It was right underneath it, right? It was certain about which one was going to hit first, and it was right underneath it the whole time, waiting for it. It grabbed it. The moment it grabbed it, what could the robot see at that point? Could it see the darker object?
Yes.
No.
No.
Yeah, good.
The line is inside the darker trapezoid. It caught the light object and it could see the dark object over there, right? The squiggly line is still inside the darker trapezoid, right? So what does it do? No hesitation. It immediately gets over there and sort of tracks it as it's falling and catches the second object. No problem, right? No problem because this is an easy one, right? At every time step, the robot could see both objects, right? This line was always inside both trapezoids. And so there was no object permanence problem. Didn't need to remember anything. Everything was in view. And there was no passing objects problem. So it's not PO, which means that the lighter object hit first, which means the lighter object started closer to the robot than the darker object in this case. Okay, let's take the same robot, put it in a slightly more difficult problem. Now we have the passing objects problem, but not the object permanence problem. I don't know if it says on here. What does the dashed line represent?
When the two objects pass each other.
Exactly, right? So it's a horizontal line, so it's telling us something happened at a particular point in time. And because we have the passing objects problem, that's the moment in which the further object is now the closer object because it's falling faster. Tell me about this robot in this situation. What's the robot doing above this line?
Its first step is to move right, because I would assume that object is closer, and then it starts to recognize that the object to the left is moving faster, or recognize, quote unquote, and moves to the left, and then moves back to the right, and then once it passes, it starts to move back to the left.
That's it, right? So
Starts to squiggle.
The robot is going back and forth between these two objects, right? It is unsure about which one is going to hit first, right? It's moving around, it's looking at them, it's comparing their velocities, right? It's not quite sure yet, right? We know it's not sure because it's not underneath any one of these. We already have seen that when it's sure, it's right there, right? So it's not sure, and it's also not sure after this happens, right? After the further one now becomes the closer one. It's still between these, and it takes it a while. And actually, it takes it quite a while, but luckily, it gets underneath that one and says, oh, yeah, right, it's going to be that one that hits first and catches it. What does it do once it catches the lighter object?
It still has the other one in its field of view, so it moves over there.
Exactly, right? Remember, it can still see the other one. Off it goes and does more or less exactly the same thing it did in this case. So you can already see that by making this environment more difficult, the robot is having a harder time with it. All right, let's look at it in an inverted environment. So now, no passing objects problem. The one that's closer is actually the one that's going to hit first. But now we've got the object permanence problem. How do you know that? You can see it from the figure.
There's a large area where the black line is not within the two trapezoids.
There is a long period here in which the black line is not inside of both trapezoids, right? Exactly. So in this time period here, the robot can only see the light-colored object. You'll notice at the beginning it also seemed to sort of not be sure what's going on. It was actually thinking maybe it was this, the darker object was going to hit first, decided. And at the moment that it captures the light object, what does the robot do?
Dips.
What's that?
Immediately just bails and goes as fast as it can.
Fast it can go, and there's no hesitation, right? It remembers, at least it remembers on which side the object is. That we know for sure, right? It immediately goes left because it knows the object is on its left. Keeps going, keeps going, keeps going. Suddenly sees it again and does its usual dance underneath the falling object and captures it, right?
Were there preliminary tests to figure out, so the robot could figure out its maximum velocity?
Yes. So there are environments you could make that would be impossible for the robot to solve, right? Two objects hit at exactly the same time at very different horizontal positions. So there's a little bit of crafting by the investigators of these environments to make sure some were easy, some were hard, but none were impossible. Okay, now let's do the fun one. We've got, we're exposing the robot to two problems. How does the robot respond?
Fantastic.
Well, it looks like it kind of prioritizes, figuring out once the object passes, it knows that it's going to hit the ground first, so it prioritizes that object, and then using the behavior from the previous example, it knows that the other one is to its right, so as soon as it catches the one that it knows hits the ground first, it just hightails it.
It's out of there, right? Exactly. Good. You're using lots of square quotes. You're becoming a good roboticist, right? We're not quite sure exactly what's going on inside the C turn N, but it looks like it's prioritizing the light object over the dark object, even though it can't see it anymore. Same thing. The moment you catch one, start heading as fast as you can for the other one. And we can see why it hightails it as fast as it can, because in some cases it doesn't have a lot of time, right? In this case, it happens to get there just at the moment that it happens. Okay, we're going to finish lecture 9 now with this environment. This one is wonderfully diabolical. Why? Why is environment 5 even harder than environment 4? Still the same thing. We still have the passing objects and object permanence problem. Jack?
The trapezoids, the field of view, I can't tell, but they either have no overlap or a very small overlap.
They have a very, very small overlap here, and they separate, the two trapezoids separate above the dotted line. What does that tell you? Why is this making things so difficult for the robot?
You can't see where object 2 is going to fall.
Not only that, there are other cases where it couldn't see that before. Why is it particularly difficult that it's above the dotted line?
Because it doesn't know which one is going to hit first.
Well, it clearly does know because it succeeded, but it was before the dotted line, which means What does that tell us? That they hadn't passed each other yet, right? So you're close, right? It definitely does know. It had to infer which one was going to hit first, even before they had passed one another. So it's not relying on this heuristic of just go for the one that's closer. It's actually somehow it's being forced to compare relative velocities. That one is for the lighter object is further away from me right now, but it's moving faster. And the two objects are moving away from one another, so I don't even have time to watch whether it passes the darker object, right? It's comparing their velocities, and then off it goes, right? You'll see that the robot is doing the right thing, right? It has to be right there. So there's a very short period in which it can see both robots, and during that very short period, it has to detect these relative velocities and make its decision very early. Chase that one, chase the further one, chase the 2 marshmallows, not the 1 marshmallow, right? And catch it, and then go and get your 3rd marshmallow. You've done a very good job. This was a very difficult environment. Right? Okay, so very minimal robots, simple fitness functions, simple environments. But I think this is probably my favorite lecture of the course because it shows the potential of this kind of approach, right? If you were to watch, well, we just did actually watch a video of this, right? It's a pretty intelligent behavior. You can see there's some memory going on there, some selective attention. We could maybe give this robot an arm and it's got to capture the robots. We could fold in the self-non-self discrimination task. We could put objects of different shape, capture round objects but avoid edged objects. We could start to, from this simple starting point, gradually layer in more and more complexity and keep evolving the robot to greater and greater levels of intelligence. Any questions about these before we move on? Yes?
Was this the final evolution, or whatever they decided was the final evolution, or was this the first evolution of it?
This was the best robot they were able to evolve, right? This is pretty sophisticated. Okay, we have 3 minutes left, so I'm just going to introduce the next topic from Lecture 10. Again, the reading for Lecture 10, this won't be on the quiz for tonight, but this is the actual research article associated with this. It gets pretty involved, so you just need to read the abstract and the introduction and the conclusions. You can read the whole paper if you want. This is a 5th building block called active categorical perception, or ACP. We're going to see ACP a number of times throughout this course. Perception, that one we know. Categorization, that's pretty straightforward. We're going to categorize the things that we perceive, but we're going to categorize them not passively by just sort of sitting back and looking at them or hitting them with ray sensors. We're going to categorize these objects actively by reaching out and manipulating them, by actually touching these objects and through action try and discriminate between these objects. There's something magical that happens when an animal or an organism or a robot physically interacts with its world, which is that in a continuous world where there aren't really any categories, look at these objects here. Look at this series of objects. There aren't really 2 categories here. There's just a spectrum of objects. But the moment you interact with objects, the way in which you interact lumps these objects into different categories. So we'll finish with this thought experiment. It's described here. Let's say I had these 11 objects. I placed one of them after the other in front of you. You have a blindfold on, so you can't see them. I place the object on the table. I ask you to take your hand palm down, place your palm on the object, and then move your palm left and right with the object underneath your palm. What would happen? If you did this 11 times with these 11 objects, what would be the result of this interaction?
Some would roll, some wouldn't.
Some would roll and some wouldn't. Remember our discussion about affordances, right? You usually use adverbs to describe objects, right? In this case, some of these objects are rollable and some are not. So suddenly, from a continuum of objects, because we're talking about interaction, a category appears, right? Most of intelligence, the cathedral of intelligence, is built on the bedrock of categorization. If you can't distinguish between the poisonous berry and the nutritious berry, or the friend or the foe, you're not going to get far in this world, right? But where do these categories come from in the first place? They come from not just the objects themselves, but how we interact with them. By actively interacting with these objects, we can perceive the categories that arise from these interactions. And on Tuesday, we will see a robot that succeeds at this task. You have a quiz due tonight, which will just be on Lecture 9, and you're carrying on with Assignment 6 or the final project. Thanks.